Good afternoon. My name is Hemery. I am assistant professor at Institut P', and today I would like to talk about strain localization and fatigue crack formation at 0001 twist boundaries in titanium alloys. This work has been carried out at Institut P' in France and at the University of California, Santa Barbara in the United States. To start my presentation, I would like to present a short overview of the two main fatigue crack initiation mechanisms that have been reported in the literature. Regarding low cycle fatigue, cracks initiate on the surface of the specimen as shown on the SEM micrograph presented on the left-hand side of this slide. The crack forms on a basal slip band in a primary alpha grain that is well oriented for slip, as shown by the high Schmidt factor for basal slip. Examination of the crystallographic orientation at the initiation alpha grain reveals a low misorientation between the C-axis of the HCP lattice and the loading direction that indicates a high stress acting normal to the basal plane and favoring crack initiation. A different crack initiation mechanism has been reported for dwell fatigue loadings because of the introduction of a load hold at peak stress in the loading waveform. The introduction of the load hold leads to a faster strain accumulation. This is shown in the plastic strain plot, again, the number of cycles for fatigue and dwell fatigue loadings. This strain accumulation is associated with a reduction in lifetime that is called the dwell fatigue life debit. For such loading conditions, crack formations proceed subsurface on a basal slip band in a primary alpha grain that is poorly oriented for slip. Such grain is called a hard grain, and the microstructural configurations favoring crack initiation are composed of a hard grain surrounded by soft grains. In these soft grains, basal or prismatic slip is easy. And during the load hold at stress, cold creep occurs, and because of strain incompatibilities across the grain boundaries between soft and hard grains, the stress level in the hard grain increases and then triggers facet formation. In spite of these crack initiation mechanisms, there are still apparently contradictory observations that are reported in the literature. These observations are generally assumed to pertain to the variety of microstructures and compositions in titanium alloys. But in order to clarify this point, we have carried out a study focusing on the fatigue crack initiation mechanism in various titanium alloys with different microstructures. We have considered Ti6242, which is a near alpha alloy, Ti64 and Ti6246, which are alpha plus beta alloys. All these alloys were considered with the bimodal microstructures that are presented on the BSE micrographs shown on the right-hand side of this slide. Ti64 was also considered with an equiaxed microstructure. All these materials exhibit quite different tensile behaviors, as shown by the stress-strain curves presented on the left. And these materials were tested in the low cycle fatigue regime. The specimens were loaded in 1 second. The peak stress is held for 1 second. The specimens are unloaded in 1 second, and the minimum stress is held for 1 second. A load ratio of 0.1 was applied, and the peak stress was set around 90% of the yield strength. The tests were interrupted before failure of the specimen in order to study the formation of the first cracks. A number of cycles between 1,000 and 2,500 was applied. Then the whole gauge length of the specimen was characterized using scanning electron microscopy in order to detect initiated cracks as short as a few microns. The very small length of the cracks ensures a straightforward identification of the crack initiation site. The number of cracks that have been noticed on the surface of the specimen is indicated in the plot of the cumulated plastic strain with respect to the number of cycles for all the tests that have been carried out for this study. The restricted number of cracks ensures that we are considering the microstructural configurations that are the most critical for fatigue crack initiation. Typical examples of such microstructural configurations leading to crack initiation are presented in this slide. The cracks are shown on the BSE micrographs here. These cracks are parallel to the basal planes on both sides of the crack, but the BSE micrographs and the inverse pole figure maps that show a crystallographic orientation along the loading direction reveal a significant misorientation between both sides of the crack that highlights the presence of a grain boundary. This is confirmed by the schematic representation of the HCP lattice on the IPF maps, and they reveal that there is a rotation around the 0001 axis across the boundary. In order to obtain additional information about the 3D crack geometry and the microstructure surrounding the crack, we have extracted thin foils using focused ion beam for TI6242 and TI6246. These thin foils were observed using a STEM detector in a scanning electron microscope. The crack in the TI6242 sample is located here. This is fib milling damage, but the crack is here. And for TI6246, the crack is located there. The basal planes are indicated by dashed lines, and it reveals that the cracks are parallel to the basal planes in 3D. And another interesting observation is the absence of grain boundary that is visible nearby the crack. That reveals that the crack forms along the grain boundary. And because of the 3D geometry of the crack, of the grain boundary, and the orientation relationships between both sides of the crack, it reveals that the crack actually formed along a 0001 twist boundary. And this was observed for all the alloys and the microstructures that we have considered in this study, suggesting a unique crack initiation mechanism. We know that the fatigue cracks usually initiate in relation to local plasticity. So we investigated further how deformation initiates and develops at these specific microstructural configurations. To do so, we carried out an in situ SEM tensile test with high-resolution digital image correlation to characterize deformation on the surface of the specimen. We consider TI64 with an equiax microstructure that has been presented previously. The sample was loaded inside the scanning electron microscope, and 4 stops have been achieved for applied stress levels between 600 MPAs and 836 MPAs. 2 regions of interest have been monitored. One region of interest is shown on the right-hand side of this slide with this inverse pole figure map showing the crystallographic orientation along the loading direction. And in order to characterize deformation, we have used a DIC code that includes discontinuity tolerant kinematics that allow in-plane slip measurement. With this procedure, we have primarily focused on strain localization at 0001 twist boundaries. In the next slide is shown the in-plane slip magnitude at the first loading step. The color indicates the in-plane displacement associated with slip activity in nanometers. At the first loading step, the first slip traces are located here, and examination of the microstructure surrounding these slip events reveal the presence of 0001 twist boundaries at these high in-plane slip values. This observation reveals that this 0001 twist boundary seemingly favors early slip activity and pretty intense strain localization. When the load is increased, the number of slip traces increases. Still, we have pretty high in-plane slip values located at 0.001 twist boundaries, but it is interesting to notice that the maximum in-plane slip value is not located at a twist boundary, it's located elsewhere. Similar observations are carried out when the load is further increased. We still have these pretty high in-plane slip values at the 0.001 twist boundaries, but these are not the maximum in-plane slip values. At the final loading step, we have found only two 0.001 twist boundaries associated with strain localization in the pretty large region that we have considered. It reveals that these microstructural configurations are very rare, and we believe that they are the most critical microstructural feature that governs crack initiation in titanium alloys. Based on this data, we have extracted the distribution frequency of the in-plane slip, and this is represented in this plot. The color indicates the applied stress value. The empty symbols indicate the overall in-plane slip distribution, while the full symbols indicate the in-plane slip distribution associated with twist boundaries only. At the first loading step, that corresponds to 600 MPas, as indicated with the green dots, the highest in-plane slip values correspond to twist boundaries, while at higher applied stress values, the maximum in-plane slip values does not correspond to twist boundaries. However, it can be noticed that the in-plane slip values associated to twist boundaries are still pretty high as compared to the overall distribution of the in-plane slip values. And that reveals that we have an early and intense shear that is located at these 0.001 twist boundaries. In the following, we wanted to understand how plasticity initiates and proceeds at these 0.001 twist boundaries. So we have deformed a TI64 sample with an equiax microstructure, the same microstructure as presented previously, up to a plastic strain of 0.2%. And we have been looking for 0.001 twist boundary that separates two primary alpha grains. We found one occurrence that is presented here. You may notice that there seems to be slip activity at the boundary between the two primary alpha grains. And we have extracted a TEM thin foil using focused ion beam at this 0.001 twist boundary. A bright field stem micrograph of the thin foil is presented at the center of the slide. Magnification of this region is shown here, and the presence of a slip step confirms the occurrence of localized strain at this 0.001 twist boundary. But careful examination of the thin foil reveals the absence of dislocation structures nearby the boundary, suggesting that shearing actually occurred along this planar 0.001 twist boundary. In order to understand why strain is localized along the boundary, we have tried to evidence the presence of composition heterogeneities, elemental segregation, or the presence of beta phase along this boundary. For that purpose, we have used EDX analysis. There is a beta phase here, and the EDX analysis revealed that the beta phase is vanadium and iron rich, while the alpha phase is titanium and aluminum rich. Similar characterization were carried out along the grain boundary, but we have not evidenced any elemental segregation at the grain boundary, suggesting that there is no beta phase along such a boundary. Additional characterization of the grain boundary structure was carried out using high-resolution TEM observations. A high-angle annular dark field micrograph is presented on the left-hand side of this slide. Magnifications of regions R1 and R2 are presented here. These magnifications reveal that there are similar atomic arrangements nearby the boundary and away from the boundary, suggesting that there is no specific phase at the boundary, such as beta phase. The basal plane stacking is presented in the inverse fast Fourier transform image that have been obtained selecting the 0002 spot in the fast Fourier transform of the high resolution micrograph. And this basal plane stacking reveals that the grain boundary plane is actually parallel to the basal plane. As mentioned previously, we have not observed any specific atomic arrangement nearby the grain boundary, suggesting that there is no beta phase, but it can be difficult to distinguish alpha from beta using -1 to -10 zone axis. So we have used an hexagonal center of symmetry parameter for that purpose. The parameter should exhibit values close to 13 in the alpha phase, while it should be 0 in beta phase because of the slight differences in the atomic arrangements. The value of this parameter was calculated in the grain on the right-hand side of the grain boundary, and these values are reported here. Values are close to 13 everywhere in the grain and nowhere close to 0, showing that there is no beta phase in this grain. Similar characterization was carried out on the other side of the boundary and revealed similar conclusions, showing that there is seemingly no beta at these boundaries. This brings me to my conclusions. We have found that the first fatigue cracks are formed at 0001 twist boundaries for various alloys and microstructures that have been submitted to low cycle fatigue loadings. This is consistent with previous observations that have been reported, including low cycle dwell fatigue loadings. This crack formation process involves shear along 0001 twist boundaries with a high resolved shear stress. No beta was found at these boundaries, and intense and highly localized plastic strain occur at low applied stress along these 0001 twist boundaries. Thank you for your attention.